Hello and welcome to today's video. In today's video, I'm going to look at the complete marking scheme of the KCSE Physics Paper 1 of the year 2015. KCSE Physics Paper 1 of the year 2015. This is a complete marking scheme. There are a few changes that I've made, especially on the paper that you will download. In the paper that you will download, on the left-hand side, you'll be able to see a navigation that helps you to look at the question and the solution as you go through the solution to the paper. And as usual, if you scroll all the way to the end of the paper, you will be able to see these video links that I've been able to put there for the purpose of just helping you to access the various topics or the various past papers as you revise for your forthcoming examination. And without further ado, let's go to the first question. In this first question, we are told that figure 1 shows part of a main scale of a vernier calipers, and we are required to insert the vernier scale to the main scale to show a reading of 3.14 centimeters. When you look at this reading here, you've already been given these 3 and these 4, and each division here is 0.1 over centimeter. So for example, this one will be 3.1, this one's 3.2. So the 0 mark on the vernier will be between 3.1 and 3.2. So that will take care of 3.1. How about 0.04? This second digit here gives us the number of the vernier scale division which coincides with the main scale division. And just to make that one clear, let's click here and we'll see the solution. And by the way, should you want to see the solution to the question, you just need to click over here and it gives you the solution. So this is 3.1. So the 0 mark on the vernier scale lies between 3.1 and 3.2. And then the coinciding division will be the fourth one. Have a look at this. This is 1, 2, 3, 4. The fourth division is the division which will coincide with a division on the main scale. With a division on the main scale. Just understand that. If you check clearly, you will not see any other division on the vernier scale coincide with a division on the main scale. So that's it about question 1. Let's go to question 2. In question 2, we are given that figure 2a shows the initial reading of a burette used to measure the volume of oil. After 50 drops of the oil were run out, the final reading was shown in figure 2b. So the initial reading was 19 centimeters cubed because the readings on a burette usually increase downwards. So although this might appear to be 21, remember this one is not a measuring cylinder. So the readings of a burette increase as you go downwards. So this being 19 and this being 21. The difference between 19 and 21 will give us 2 centimeters cubed. That is the volume of 50 drops. So to get the volume of 1 drop, we need to divide that 2 centimeters cubed by 50. And again, the solution is very easy here. And this is what we get. The volume of 1 drop is equals to the volume of 50 drops divided by the number 50. And we get 0.04 centimeters cubed. Let's go to question 3. In question 3, we are given that a spring extends by 6 centimeters when supporting a mass of 0.06 kilograms on Earth. When the spring is used to support the same mass on the moon, it extends by 1 centimeter. This shows that the weight of this mass on the moon is less because it produces less extension. Determine the moon's gravitational field strength. There are 2 points we need to understand here. The spring constant does not change. It has the same value on Earth as on the moon. The other physical quantity that does not change is the mass of the object. The mass remains constant. So if we can be able to determine the spring constant of that spring on Earth, we can calculate the spring constant on the moon. And that means the force which will produce this much extension on the moon is actually the weight of that object on the moon. So if we get that force, we will get the weight of the object on the moon. If we divide that weight by the mass of the object, then we are going to get the gravitational field strength on the moon. Again, let's quickly look at the solution. So the spring constant is weight on Earth divided by the extension on Earth. This will be the weight of the object on Earth. How do I get weight from 0.06 kilograms? I just need to multiply 0.06 kilograms by the value of the gravitational field strength on Earth, which is 10 Newton per kilogram, and I get 0.6 newtons. And then I convert this extension of 6 centimeters into meters by dividing these 6 centimeters by 100. And when I do that, I get the spring constant to be 10 Newton per meter. We have already agreed that the spring constant is the same on the moon as on Earth. So calculating the same spring constant on the moon, we will get spring constant is equals to weight on the moon divided by the extension on the moon. So K will be equal to 10 Newton per meter, which is the weight on the moon divided by the extension on the moon. Once we get the weight on the moon at 0.1 newtons, to get the value of the gravitational field strength on the moon, we just need to divide that weight by the mass of the object. Remember, gravitational field strength is weight divided by mass. Or you can say mass is equals to mg. And of course, we get the value of the gravitational field strength on the moon as 1.67 Newton per kilogram. Let's go to question 4. In question 4, we are asked to state two factors that determine the pressure at a point in a liquid. Of course, this one is direct. One of them is the vertical depth h of the point from the surface of the liquid, and the other one is the density rho of the liquid. There isn't much to that. The only point we can add here is since we write pressure is equals to rho hg, you find that there are three physical quantities which are used to calculate pressure at a point in a liquid, but the g is the gravitational field strength, so it will only be a factor if the gravitational field strength changes. But here it is assumed we are looking at factors which affect pressure at a point in a liquid on a given planet, like for example Earth, in which case the value of g is constant throughout. But just in case it changes from one planet to another, or to a big height where the value of g changes, then definitely g becomes a factor. Let's look at question 5. In question 5, we are given that a student wearing sharp pointed heeled shoes is likely to damage a soft wooden floor. We are required to explain this observation. Now, why does that happen? You have to remember that sharp pointed heeled shoes have got a very small area of contact. So the weight of the student will produce a very high pressure, and this pressure is the one which is going to penetrate the soft wooden floor and therefore produce some damage on it. Again, the explanation that I expect is this one. Sharp pointed heeled shoes have a small area of contact, so the idea of small area of contact must come out, so that when you say that the pressure exerted by the weight of the student on the floor is high, then you are justified. Because we are looking at factors affecting pressure in solids, one of them is area of contact, and the smaller the area, the higher the pressure. The higher the pressure, the more penetration effect that object produces on a soft ground. Let's look at question number 6. In question 6, we are given that the figure 3 shows the arrangement of molecules in the 3 states of matter, and we are asked to name the process represented by the arrow here. And this, of course, is solidification. Solidification. And in part B, we are asked to state the reason for the arrangement of molecules in state 3. State 3. Why these molecules are far from each other. And this is because the intermolecular forces of attraction are very weak. These intermolecular forces of attraction are usually referred to as cohesive forces. So they are very weak in gas state compared to solid and liquid state. And that takes us to question 7, where we have this question here. Actually, I've not gotten the solution for question 7 because I think it required a diagram and I could not be able to locate that diagram. So let's go straight to question 8. In question 8, we are given that the figure shows a uniform metal rod. I want to put some emphasis here. This word here, uniform. Uniform metal rod. We are told that it is balanced at its center by different forces. Balanced at its center. Again, this one is important because if it is balanced at its center, there would be no need to know its weight or to know the position of that center of gravity. The only advantage is that it helps us to know that this pivot divides this rod exactly into 2 equal parts. Now, in some other situations, you find that we always want to show the weight of the object when we are told that the object is uniform. In this case, it does not matter because even if we are to show the weight of the object at this point and the pivot is placed at that point, and then we take moment about the pivot, then any force which acts through that pivot is just eliminated automatically. So this is how the solution looks like. We take moment about the pivot, about this pivot. So clockwise moments will be equal to 8 newtons times this distance here. And the anti-clockwise moment will be, the sum of the anti-clockwise moment will be 4 times this distance plus this distance here, which is 50 times t. So notice that when we state the principle of moments, we don't just say clockwise moments equals to anti-clockwise moments. We talk about sum of clockwise moments is equals to sum of anti-clockwise moments. Like for instance, in this case, we are able to see that there is only one clockwise moment. No problem with that. So we can say clockwise moment. But when it comes to the anti-clockwise moments, there are 2 of them. There is the moment due to the 4 Newton force acting at this point, turning the system in the anti-clockwise direction. And there is t acting again in the anti-clockwise direction. Of course, don't be deceived by the fact that the 4 Newton force and t are on opposite sides of the pivot. Despite this fact that they are on opposite sides of the pivot, they tend to turn this plank in the same direction, which is anti-clockwise. And of course, when you manipulate these figures, you get t to be 3.6 newtons. You can always counter check some of the values I'm getting here, but the moment you got the concept straight, then there is no problem with that. Let's go to question 9. Question 9. We are given that figure 5 shows air flowing through a pipe of different cross-sectional area. 2 pipes A and B are dipped into the water, A and B. Of course, you find that these are manometers. This one is the first manometer. This is the second manometer. And the fact that this column of water rises that high, it shows that the pressure at this point is lower than the pressure at this point. So the pressure difference between the 2 points is the one which supports this column of water. So definitely the pressure at this point is lower than the pressure at this point. Now, why is that the case? You find that the speed of the air in this narrow tube, because of the smaller cross-sectional area, the speed is high, but in this section of the tube, the speed is low because the cross-section area is big. The other point is this: wherever fluids move with a high speed, pressure is reduced in that particular region. So we can tell that pressure above tube B here, it is lower than pressure above tube A. So there is a larger pressure difference here between this point and this and the surface of this liquid, and that pressure difference is the one which forces the liquid to rise up this tube. The pressure difference here is small, while the pressure difference here is high. So that is the explanation that I would give to the difference in the levels of the water in A and B. However, let's look at the solution that I had written here for you. And this is it. So let's read it together. A and B are manometers. Air has a higher speed in the tube with smaller cross-sectional area. The pressure of the air in the narrow tube is lower than the pressure of the air in the tube with wider cross-sectional area. The atmospheric pressure acting on the surface of the water pushes water to a greater height in B than in tube A because the pressure is high. Okay, over here the pressure difference is high. Here, low pressure, high pressure. But each one of these two pressures is lower than atmospheric. But where is the pressure difference highest? It is over here. Since the pressure difference is highest, this liquid is going to rise to a bigger height. Okay, let's go to question number 10. In question number 10, we are given that a balloon is filled with hydrogen gas and then released into the air. It is observed that as it rises higher into the air, it expands. Explain why it expands. Of course, we know that air pressure decreases with altitude. And so the pressure difference between the air inside the balloon, which was originally slightly greater than atmospheric pressure, remains at that value. So if we reduce the pressure outside the balloon, then that pressure difference is going to make the balloon to expand. So this is it. The pressure due to the atmosphere on the outside of the balloon decreases with altitude. Altitude is the vertical height above sea level. The pressure difference creates a resultant force which makes the balloon to expand. So the explanation is just as simple as that. Let's go to question 11. A person carrying a heavy luggage using one hand leans away from the luggage. State the reason for this. Of course, this question comes in when we are studying the position of the center of gravity and how to determine stability of objects. So let's look at the actual answer here. So this action is to shift the position of the center of gravity so that it remains within the base support area. It's important. It's important to realize that. The fact that one leans in the opposite direction is an attempt to shift the position of the center of gravity so that if we were to draw the vertical line from the center of gravity, that vertical line will pass through the base support area of the object. So the idea is to shift the position of the center of gravity so that the vertical line from the center of gravity always remains within the base support area. Let's go to question 12. In question 12, we are told that figure 6 shows a glass tube with water fitted with the two identical thermometers A and B. It is heated as shown. State with the reason which of the thermometers shows a higher temperature here. So when we heat water at this point, we'll find that the water above this level here will be heated by convection currents. Convectional currents are going to take place. But the water below that point will not get heated, because when water is heated, it expands, becomes less dense, and rises. So it cannot sink to the bottom. When it rises, it carries heat with it. So the convectional currents are just going to be established between this point, like that, and none of that heat will travel this way, because there is no way less dense water can sink downwards. It's already at the top. As far as this horizontal line here is concerned, this water here is already at the top. So heating it and making it less dense will not make it move down. It will just make it rise upwards like that. The only way this water at this point where we have thermometer A can get heated is by conduction. But water is a poor conductor of heat, so this does not happen. So let's look at the solution that I had written down here, and this is it. Thermometer B will show a higher temperature rise. Why? Heat reaches this thermometer by convection through the water. Heat can only reach A by conduction, but this does not happen because water is a poor conductor of heat. So that answer was just as simple as that. Let's go to question 13. In question 13, we are asked, mechanics is one of the branches of physics. State what it deals with. Of course, this is a very simple question. It's about branches of physics. And this branch of physics deals with the study of motion of bodies under the influence of forces. So don't forget to study the other branches of physics, because any one of them can be asked. At the same time, don't forget to study the relationship between physics and other subjects, because again, a question from 1 mark can be set in that area. So 2 areas, branches of physics. Know the name of that branch and a simple description of that branch. And then when it comes to the relationship between physics and other subjects, just have a simple statement that describes a simple relationship between the 2 subjects, physics and other subjects that you are taking. Let's look at question 14. In question 14, we are given this ticker tape here. Figure 7, it is drawn to scale. But because I could not be able to do that, what I did is to give you distances here. After all, what is required is for you to know the method of how you can go about calculating the acceleration of the object. So it shows a section of a tape after passing through a ticker timer operated at a frequency of 50 Hz. This is important because it allows us to calculate the time taken by this ticker timer to cover the distance between any 2 dots. So if you get 1/50, which is the periodic time, it is going to give you 0.02 seconds. So this object takes 0.02 seconds to travel through a distance equal to this much. It also takes 0.02 seconds to travel this distance here. So here it is traveling slowly, and here it is traveling very fast, because you can see the distance covered here is bigger than the distance covered here, despite the fact that the time taken is the same, which is 0.02 seconds. So let's see the first part. We are required to determine the velocity between P and Q. P and Q. Of course, the velocity is just this average distance, which is 0.08 meters divided by 0.02 seconds. However, let's look at the solution to that. And this is how I did it. The time to cover the distance between the 2 particles would be given by 1/f. This one should be 1/f. I think I made a mistake there. Let me just correct that. That one should be 1/f. That is 1/frequency in order to get the periodic time. Actually, what we are working out here is the periodic time, it ought to look like that. So periodic time is 1 over f, which is 1 over 50, which is 0.02 seconds. Like I've explained, this is the time taken for the object to cover a distance equal to the distance between any two dots. So the speed PQ, that speed PQ is going to be equal to that distance, which is 0.08 meters divided by 0.02, and I get 4 meters per second. How about the speed XY? XY is a distance of 1 centimeter, which is 0.01 meters. How do I get that speed? Of course, it's very simple. It is 0.01 meters divided again by 0.02. I get 0.5 meters per second. The other part is to determine the acceleration of the trolley. Now, this is it. Given that this is the direction of motion of the trolley, it means that this trolley was connected here, so that when it pulls this tape, this becomes the first part to go through the ticker timer. So this part here, XY, occurred later. So because this is the first part which went through the ticker timer, the speed we have calculated here, which is 4 meters per second, is the initial speed, while the final speed is at this point. So we've got U and we've got V. Next, we need to calculate the time taken for this speed to change from 4 meters per second to 5 meters to 0.5 meters per second. And that time is usually given by this. So you count the number of complete dots or spaces between the dots, 1, 2, 3, 4. And then when you come to this one, you are going to go into half of that distance, and then into half of this distance, and you will get the time here will be half of this, which is 0.01, and the time from here to the middle here will be again half of this. So if you add this half and this other half here, actually you get 0.02 seconds. So that having been taken care of, you now multiply 1, 2, 3, 4 by 0.02, and then you're going to add another 0.02. So you understand why the other 0.02 is added, because there is a half here and there is a half here. So that is how you get the time for the velocity to change. So this is it. Time t for velocity to change will be 0.02 times 5. Why times 5? It is because it is this one, 1, 2, 3, 4, and then a half and a half. That makes 5. So that gives us 0.1 seconds. And of course, now we use this equation. A is equals to V minus U over T. We substitute V, which is 0.5 minus 4. We get that, and we find that the acceleration has a negative sign of 35 meters per second squared. Because we've been asked to calculate the acceleration, we leave it as such. We leave it as such with the negative sign. But if we had been asked to calculate the deceleration, then we will say the deceleration is equal to, this time we forget about the negative sign and just quote 35 meters per second per second. So that's it about that part. Let's go to the next part here, where we are told that two bodies of mass 5 kg and 8 kg moving in the same direction with velocities of 20 meters per second and 15 meters per second respectively collide inelastically. When objects collide inelastically, it means that kinetic energy is not conserved. Kinetic energy is not conserved. It's only momentum which is conserved. Determine the velocity of the bodies after collision. So they are going to coalesce. They are going to stick together. So this is the situation that I have. In this question, we will apply the principle of conservation of momentum, which states that total momentum of the system before collision is equal to total momentum of the system after collision. Now, because they are moving in the same direction, and when it comes to adding their momenta, it becomes very easy. So it is this momentum, which is mass times velocity, plus this other momentum is equals to, because the two bodies stick together, I've got to add their masses together and multiply by the common velocity. And when you definitely manipulate that, you get a common velocity of 18.5 meters per second. So you realize that the one which was moving faster is slowed down, while the one which was moving slowly is speeds up. So definitely this one must have been behind this one for this one to be able to catch up with it. Let's go to question 15. In question 15, we are given that part A, figure 8, shows a 200-gram mass placed on a frictionless surface and attached to a spring, like this. The spring is compressed and released. Given that the elastic potential energy of the compressed spring is this much, determine the maximum speed with which the block moves after it is released. In this question, we are dealing with a compressed spring. The amount of energy stored in this spring is called elastic potential energy, and as soon as this mass is released, then it's going to spring from that mass. We are asked to calculate that initial speed. That means that the elastic potential energy of the spring is converted into kinetic energy of this mass. So let's see how we handle that first part, where we are asked to calculate the maximum speed with which the block moves just after it is released. So elastic potential energy stored in the spring is converted into kinetic energy of the mass. So we already have that energy. It was given here. So we equate it to a half mv squared, and we get our speed to be 0.5 meters per second. Next, we are given this part here where we are told that in a wheel and axle system, state the advantage of having a large wheel diameter compared to the axle diameter for a frictionless system. So here I want us to look at the solution straight, because I have a diagram that I'd like us to consider. So this is the wheel and axle. This diagram was not asked. I've just included it here so that we can be able to get the idea of what the wheel and axle system is all about. So the load is usually connected to the string or the rope which wraps itself around the axle, while the effort or the force that we apply is usually applied here. There is a string here that is in this groove. There is always a groove here, and there is a string that we pull, so that as this wheel turns, the axle is also going to turn. If we look at this diagram from the side, this is what we are going to see. So the effort, this system turns about this point, and you can see that the effort produces moment about this axis. The load also produces the same moment. So at a certain point where the system is just about to turn, you find that the moment due to the effort will be equal to the effort times the distance r. It will be equal to the load times the distance r. So this helps us when this r is big, and therefore we are being asked, why is it that the effort is connected to the larger wheel? It's because we want to reduce the value of the effort while getting the same amount of turning effect by increasing the distance. When we increase the distance, we can comfortably use a small force to lift a bigger force. So this is the explanation that I thought would be very suitable. The larger radius serves to increase the moment due to the effort. because of that large distance. So a small effort can be used to produce a large moment, which when divided by the small radius gives a large value of the load. Okay, let's look at part C of the same question. A body is released from a height h. Sketch the graph of potential energy. Here I'm guessing it is gravitational potential energy, because there are two types of potential energies. One of them is gravitational potential energy, the other one is elastic potential energy. So we are supposed to plot a graph of gravitational potential energy, against the kinetic energy as the body falls to the ground. So let's see what kind of graph we get. And this is the graph that we get. So potential energy is very high at the highest point of this height, of course, and as the height decreases, kinetic energy of the object is going to increase. So this is basically what happens. So kinetic energy is very high at just before the object strikes the ground, in which case now the potential energy is just equal to 0, while potential energy was very high just before the mass was released. Let's look at 15D. We are told that in this question, the figure 9 shows a hydraulic lift system. So the radius of the small piston is 3 centimeters, while that of the large piston is 9 centimeters. A force of 90 newtons is applied to the smaller piston. Of course, this being a hydraulic system, we know that when this effort is applied to this piston, it produces pressure here, which is transmitted throughout this enclosed liquid, according to Pascal's principle. And we find that the same pressure that was exerted here is exerted by the liquid on this piston, which supports the load. So you can see that this one is a larger piston, this one is a smaller piston. So we can be able to calculate the mechanical advantage of the system, the velocity ratio of the system, and finally calculate the efficiency of the system. So in part 1, we are asked to determine the maximum load that can be lifted. So let's look at that. Of course, it comes from what I've just said. F1 over A1 is equals to F2 over A2. F1 was 90 newtons. A1 is the area of that piston, which is pi times 3 squared. Okay, I never bothered to convert centimeters into meters because I knew if I do that on the left hand side of the equal sign and I do the same on the right hand side, that effect will just cancel out, and it is as if I never attempted to convert in the first place. So it is equals to the F2, which is the load, over this. Calculating that, I get a load of 810 newtons. We are required to calculate the efficiency of the system. I've already said that for us to determine the efficiency of the system, we need to get the velocity ratio, which is the distance moved by the effort, or the effort piston, divided by the distance moved by the load. That will be the velocity ratio, while the mechanical advantage is load over the effort. And you can see we've already gotten our load, 810. The effort is 90, so we can get the mechanical advantage directly from there. So let's look at the solution. So mechanical advantage is equal to 9. Velocity ratio is given by the radius of the larger piston squared divided by the radius of the smaller piston squared. We can be asked to show this, and it is easy to show this because all you need to do is just to say the volume when this piston moves through a certain distance, which is equal to the effort distance. This one moves through a different distance, which is of course smaller but vertically upwards. The amount of liquid here that is displaced is equal to the volume of the liquid here that is displaced. And you know, the volume here will be the cross-section area times the distance moved by the effort by the effort, while the volume here will be the cross-section area times the distance moved by the load. So when we equate the two, we are going to find that the pi's are going to cancel out, and eventually the velocity ratio is given by capital R squared over small r squared, which of course gives us 9. I found this question a bit strange because the value of the mechanical advantage and the velocity ratio is the same, in which case I got an efficiency of 100%. So let's move over to question 16. In question 16, this is about heat. We are told that figure 10 shows an incomplete setup that can be used in an experiment to determine the specific heat capacity of a solid. This value here, specific heat capacity of a solid of mass m by the electrical method. So this must be an aluminium block, for example, or a copper block with the holes which have been made, drilled into the block in order to accommodate the heater. The other hole accommodates the thermometer. Of course, there is always some oil which is put here to provide good thermal contact between the block and the bulb of the thermometer to enable the thermometer to measure the temperature of the block. So what is missing here, I guess, would be I need to connect a voltmeter across this heater, and I need to connect an ammeter so that I can measure the current, the steady current which flows through the heater, and the voltage across it. So this is how that complete diagram would appear to be here. So we need an ammeter and a voltmeter. So that part was just as simple as that. This one ought to have read other than temperature. Let me just correct that. Other than temperature, state the 3 measurements that should be taken for 3 marks. What are these 3 other measurements? We need to take the voltage across the steady voltage across the heater, as well as the steady current here. And also, we also need a stopwatch to measure the time taken for the temperature of the block to change from a certain value into a higher value. So let's look at it closely, and we find that we need to measure. Oh, I forgot about the mass of the block, because how else would we be able to determine the specific heat capacity if we don't know the mass of the block? Unless maybe it was not mentioned in the question. Yes, it was not a solid of mass m. Fine, maybe this statement, a solid of mass m, may mean that maybe the mass of the block was given. However, that statement is not very clear. That is why measurement of the mass of the block is important. We can also measure the power or determine or record the power of the heater. And if that is not possible, then we need to know the current, the steady current through the heater and the voltage across it in order to use power is equal to IV. And of course, time t taken for the temperature to change by delta theta. Part 3, we are told that the final temperature was recorded as theta. Write an expression that can be used to determine the specific capacity of the solid. So this having been the final temperature, we need to have recorded the room temperature, because this object is being heated from room temperature, and the change in temperature would be theta minus the room temperature or the initial temperature. So let's look at the solution. The electrical energy provided by the heater would be equal to the heat absorbed by the solid. Of course, this would be power times time is equals to mc delta theta. Like I said, in the absence of this power, we would put I times V. I times V. That is why we needed to record the current and the the voltage and the steady current which is flowing through the heater. Let's look at this other part here. State 3 ways of increasing the sensitivity of a liquid in glass thermometer. And there are these ways here. Use thermometric liquid of a low specific capacity. That will increase the sensitivity. Use a thermometer with a large bulb. It will increase the sensitivity. And the bore of the capillary must be very small. So don't confuse these factors with the factors which must be considered when we want to make the thermometer to be quick acting. If we were to make the thermometer to be quick acting, instead of using a large bulb, we would use a small bulb. There is some difference here. And of course, the wall of the bulb must be very thin in order for the heat to travel very fast from the liquid into the thermometric liquid. Alright, we are coming almost to the end. Let's look at question number 17. In question number 17, we are told that figure 11 shows a graph of pressure P against volume V for a fixed mass of gas at constant temperature. In the space provided, sketch the corresponding graph of P against 1 over V. And this is it. Pressure against 1 over V, we're going to get a straight line through the origin. So I believe that graph, which I never included here, was sort of curving like this, and therefore when I make 1 over V, when I plot pressure against 1 over V, we get a straight line through the origin. You can check in the question paper to confirm that. Explain the pressure law using the kinetic theory of gases. Of course, for us to explain the pressure law, I think it is important that we state the law first. So, pressure of a fixed mass of a gas is directly proportional to its thermodynamic temperature, provided volume is kept constant. So it is this law that we want to explain, use in molecular terms. When a gas is heated, its molecules gain kinetic energy and move about faster. If the volume of the container is kept unchanged or is kept the same, there is something that I'm missing here. If the volume of the container is kept constant, the molecules will bombard the walls many more times per unit time because they are moving much faster. So the frequency at which they bombard the wall will increase, and the speed with which they bombard the wall will also increase. So this means that they are going to bombard the wall with greater momenta. Momenta is plural for momentum. The total rate of change of momentum will therefore increase. You know, rate of change of momentum is actually force. Therefore, the resultant force per unit area, which is pressure, will therefore increase. And that is how you explain that question. Part C of question 17, we are told that 20 centimeters cubed of a gas exerts a pressure of 760 millimeters of mercury at 25 degrees Celsius. Determine the temperature of the gas when the pressure increases to 900 millimeters of mercury and the volume reduces to 15 centimeters cubed. So here we know that this is V1, this is P1, and this one is T1. Of course, we have to convert it into Kelvin. Now we are supposed to determine T2, given that P2 is 900 millimeters of mercury and V2 is 15 centimeters cubed. The only thing that you've got to be careful here is to ensure that temperature is in Kelvin. When you use P1, V1 is equals to P2, V2, you have to ensure that this temperature of 25 degrees Celsius is in Kelvin. And that is what I have done over here. Of course, this one is not multiplication. Should not have been multiplication. It should have been a plus sign. It's not multiplication, so we put a plus sign over there, because here I'm trying to convey the fact that I'm converting 25 degrees Celsius into Kelvin. So I hope this one would have, this one is 398, yes, 398 times 900 times 15 divided by 760 times 20 gives me 353.5 Kelvin, and this will be 80.5 degrees Celsius. You can confirm this calculation by yourself now that you have seen I have made that simple correction there, but it's not, I believe when I was calculating it, I took care of it. It's only that here instead of putting plus, I put a multiplication sign. Figure 12 shows the path of a light ball projected horizontally. This path here is the path of the light ball. The red one is the answer. The ball is then made to spin in air in an anti-clockwise direction. Anti-clockwise direction like this. On the same axis, sketch the new path of the ball. So it will rise slightly like that and then begin to fall downwards, and it will cover a bigger range. This R will be much bigger. Now, what is the explanation? Explain how the ball attains the new path. Let's see about that explanation. As the ball spins in the anti-clockwise direction, it drags air along with it, which opposes, let me just remove this space here. Yes. So, as the ball spins in the anti-clockwise direction, it drags air along with it, which opposes the relative motion on the lower side of the ball. The streamlines on the lower side are spread out more. On the upper side, the dragged air is in the direction of the relative motion, resulting in an increase in speed and consequently a decrease in pressure. So this is what we are saying. Because this one is rotating like this and the ball is moving that way, if it is moving this way, then the streamlines are moving in the opposite direction, and it is rotating in the opposite direction. You find that here the streamlines are will be in a direction which is in opposition to the rotation of the ball. So here the speed of the streamlines is going to be reduced, but here the speed of the streamlines is going to be enhanced because the ball is rotating in the same direction as the streamlines. Hence, where the air or the fluid moves fast, there is low pressure compared to where the speed is low. So there is low pressure, high pressure. This pressure difference is the one which exerts a force upwards, a resultant force on the ball upwards, and that is why it rises. So that explanation is as given here. You can again go through this explanation just to satisfy yourself that you know what that is all about. Let's look at question 18, which is the last question in this paper. A. Figure 13 shows a pendulum bob suspended by a thread moving in a horizontal circle, like this. So this one is what we refer to as a conical pendulum. Name the two forces acting on the pendulum bob as it moves. Of course, one of them is the weight of the bob, which is the gravitational force on the bob, and the other one is the tension in the string. So it's just as simple as that. Weight of the bob, or the gravitational force, and tension in the string, or tension in the rope. Part 2 of A. State what happens to each of the forces when the angular velocity of the pendulum is increased. This is what happens when we increase the angular velocity. It means that this mass must be moving at a higher speed. Okay, so of course the weight of the bob remains the same because that one does not change. Weight is equal to mg, so that one does not change, but the tension in the string is going to increase. Why does it increase? We have not been asked to explain, we've just been asked to state what happens to the forces. So weight of the bulb, gravitational force, there is no effect, while tension in the string, it's going to increase. Part 3. State 2 applications of uniform circular motion in daily life. What are these 2 applications? So the 2 applications are as follows. They're not many, at least according to this particular question, but in everyday life situation, situations or applications of circular motion are very, very many. I've just quoted a few. It depends on what you state and how you state it. Like, for example, cars moving around a circular track is a good example, or an athlete rounding a bend on the track is another example. Let's look at part B of question 18. We are told that figure 14 shows a block floating in water. Now the question is, when the water is heated, it is observed that the block sinks further. Explain this observation. Why does that happen? This is why it happens. When the water is heated, it expands and becomes less dense. When water is heated, it expands and becomes less dense. The upthrust on the block reduces because the weight of the block is reduced. I think this one should be the upthrust on the block reduced because the weight of the water displaced reduced. Why does it reduce? Because of the decreased density. So here I'm going to make some corrections there. Since the weight of the block is equal to the upthrust, the block has to sink more into the water in order to displace extra volume of the water, which would restore the upthrust to a value which is equal to the weight of the block. So the weight of the block does not change. Remember that. It's just a mistake that I've made here. So as I read these answers, I'm able to see the kind of mistakes I've made too. So the correct answer is, when the water is heated, it expands and becomes less dense. That one is a fact. The upthrust on the block reduces because the weight of the water displaced reduced on account of the reduction in the density. Since the weight of the block is equal to the upthrust, or must be equal to the upthrust, the block has to sink more into the water in order to displace the extra volume of the water, which would restore the upthrust to a value which is equal to the weight of the block. And that brings us to the end of this particular paper. Go ahead, download the paper from the video description. Try to do it before you go through this video, or after you've even gone through the video. Try to see whether you can be able to recall some of the answers by trying to rewrite the answers. And don't forget to go to the end of that particular paper where I've put links to other questions which are going to be of use to you when you are revising for your forthcoming examination. Otherwise, until next time when I look at another video, it's bye-bye.